I'd now like to introduce Stephen Wilbur from Agilent, who's going to talk to us a bit about developments over the past 25 years and maybe some things for the future as well.
Thank you very much. First of all, I'd like to thank the people at RC for inviting me and giving me the opportunity to be here. And certainly all of you in this room, this is just a fantastic turnaround. So thank you very much. It's interesting for me to be able to talk a little bit about the history of ICP-MS and be the only person that's talking about it from a quadrupole standpoint. Generally, everyone's talking about the history of quadrupole ICP-MS, and then the high-res people are sort of in the minority, so I feel a little bit outnumbered today. We've heard a little bit about the initial development of ICP-MS back in the early 1980s by Alan Gray and Sam Howell and those people, but what most of us don't know is that there was kind of a parallel development happening in Japan that really outside of Japan was relatively unknown at the time. So we're going to talk about this sort of development or this innovation of ICP-MS that really began in Japan and then advanced through the rest of the world. So it goes clear back to 1984, the initial paper by Jarvis and Gray and Sam Howell talking about the coupling of a quadrupole ICP-MS or a quadrupole mass spectrometer to an inductively coupled plasma source. And those early instruments, as we know, really surprised everyone in the performance that they were able to achieve. The early instruments gave very, very good sensitivity. At the time, as high as, this doesn't sound like so much now, but at the time 1 megahertz or 1,000,000 counts per second per ppm was very, very good sensitivity with backgrounds in the sort of range of 5 to 50 counts per second. But the early instruments had some limitations that really we've been working to solve ever since. And those limitations were related to interferences mostly from polyatomic ions. The high resolution people have a good solution to that. Relatively poor matrix tolerance compared to other techniques at the time, and relatively limited dynamic range. And so since that time, really in the ICP-MS community as a whole, and certainly at Agilent Technologies, we've been working to really try to reduce or eliminate those limitations. So early on, there were some of these early papers by Sam Howell and Alan Gray, and people in Japan were reading these papers. A person named Kenichi Sakata particularly, he was going to these early 1980 winter conferences, and he went to one of those, and he scratched his head and said, I think we could build one of those. So he went back to Japan, outside of Tokyo, and he looked around in the closet and found some parts, and he put together this pre-benchtop ICP-MS back in 1984 and 1985. Okay, so this was the first prototype ICP-MS built in the Yokogawa factory in Japan. So a couple of years later, they put some sheet metal around the outside of that instrument, called it the PMS 100. For obvious reasons, we couldn't market that in the US. And they built 3 of those, and those were sold in Japan. And I believe one of those is still operating to this day. So these instruments were innovative in that they pioneered the first use of full digital or computer control of ICP-MS. So this was the first fully digitally controlled ICP-MS anywhere in the world. So that was in 1987, 88, and 89. In 1994, Hewlett-Packard approached Yokogawa Electric and proposed a joint venture, and the idea was to take Hewlett-Packard's knowledge and experience in benchtop GCMS and benchtop mass spectrometers and combine that with Yokogawa's experience in ICP plasma emission sources and to create the world's first benchtop ICP-MS. And you can see that right here. This is the development team for the HP 4500. Almost all of those people still work in the factory at Hachioji. They just have gray hair like me. But that was back in 1994. So the HP 4500, and it happened that since we were talking about semiconductor a little bit earlier, the semiconductor boom of the 1990s, the sort of logarithmic growth of semiconductor manufacturing in the 1990s, was kind of a perfect fit for the HP 4500. The HP 4500 was small enough to put in a clean room, and it had the ability to measure a handful of elements that were really important to the semiconductor manufacturing industry that couldn't previously be measured at low levels by ICP-MS. Those elements are really sodium, potassium, calcium, and iron. And those are what we call the cool plasma elements, elements that have very high backgrounds or elevated background in an argon plasma. So the HP 4500 pioneered the use of cool plasma technology to be able to give us sub-ppb detection limits for those elements. And around 800 of those instruments were sold largely to the semiconductor manufacturing industry. Oops. So we used a technique called shield torch technology to achieve this cool plasma performance. And it's a very simple metal device that isolates the plasma from the load coil, and it reduces that secondary discharge that causes secondary ionization of polyatomics. What we didn't know at the time, and we gradually learned, is that also by minimizing secondary discharge in the plasma, that minimizes the energy distribution of the ions, gives us much better ion focusing and therefore much higher sensitivity. So as we began to learn some of the advantages of this shield torch, we realized that we could apply it to other things besides cool plasma. So we started to put shield torch technology in all of our instruments, and we took advantage of the second advantage of reducing the energy distribution. And I'll just spend a second on this because this is really the basis of all Agilent instruments at this time. And it's a concept called kinetic energy discrimination, and it's the way that we can reduce polyatomic interferences generically without knowing what they are, without knowing what the matrix is. And it's very, very simple. We assume that we know that polyatomic interferences have the same mass and charge as our aniline ions. They also have the same kinetic energy as they go into the mass spectrometer. Kinetic energy is determined by the kinetic energy of the argon. And if we can narrow this energy distribution as narrow as possible, and then we can introduce these ions into a collision cell where each of these ions, both the aniline ion in green and the polyatomic ion in red, we can introduce those to a cell that's charged with helium gas at a relatively high pressure. And every time one of these ions collides with a helium molecule or a helium atom in the cell, it loses a little bit of energy. It slows down. It gives some energy to the helium. The polyatomic ions are big. The aniline ions are small. So the polyatomic ions will collide more often. And every time they do, they lose a little bit of energy. And so by the time these two populations of ions get to the exit of the cell, the polyatomic ions have slowed down a lot. The aniline ions have slowed down less. And then if we apply a positive potential at the exit of the cell, we can block the polyatomic ions from leaving the cell. We can allow the aniline ions to go through. So we've separated them based on their energy. So it's a very simple technique, and it relies on minimizing this energy distribution, which is what we use the shield torch for.